present the fourth use case. To begin with, I work at one of the 74 Fraunhofer institutes called FOKUS. It's an institute for open communication systems. Here on the right-hand side, you can see our building in Berlin-Charlottenburg. And in terms of our topic, open communication systems, we are concerned with many different topics and fields of applications. One of them is quantum computing, and in terms of quantum computing, our focus is to develop a programming language for quantum algorithms, a high-level language that is called Qrisp. Here you can see the front page of our web page, crisp.eu. And compared to other programming packages, Qrisp offers several interesting features. One is you can use arithmetics and variables. For linear algebra problems, you can do block encoding to test your algorithms on different backends. We have an interface, and you can also, for larger problems, use a simulator to test the performance of the algorithms. Further, you can use quantum variables in order to have a fast compilation of the underlying circuits. We implemented the JASC integration. And in order to have an efficient data management, we have a modular structure and an efficient memory management. Here's one typical Qrisp code for a very simple problem. It just computes the problem 3 times 4. So in our case, when you use Qrisp, you proceed actually as for any other standard programming language. You assign 2 variables, or to define 2 variables A and B, you assign 2 different values, 3 and 4, and then you use the standard star operator as you would do in standard Python. And as a comparison here on the left-hand side, you see Qiskit. Here the handling of the same problem is a little bit more complicated. You first have manually to assign quantum registers, and then do in a rather more complicated way the assignment of 3 and 4, and then call the multiplier to exert the operation. One thing you should also note about quantum variables is the following, that compared to standard variables, and since we are in a quantum world, we have to think with probabilities and superposition. So in this example here, I defined a quantum variable A attending 3 different values all with probability 1/3, and another variable B. And then also the difference to standard operations when you use, for example, plus, when you add A and B, you obtain not a single result, but a superposition of different results here ranging from 2, 3, and 4. Okay, what's also very important in terms of cryptography is maybe not in a NISQ area, not directly to simulate a certain algorithm on a real hardware or with a simulator, but to do for the future perspective resource estimations. And what you see here on the left-hand side is actually the quantum part of Shor's algorithm, which we know is the problem of finding the order of a periodic modular function. And what you see here on the right is the count of all the different gates that are needed for, let's say, relevant key sizes for RSA. So we estimated how costly it is to decompose or to do the quantum part for a bit size of 2048. And you see, you require an enormous amount of gates, and up to now we are far away from being able to attack a relevant RSA key. So within Pico React, we were responsible for the third package, benchmarking of PQC algorithms. And in order to shorten the presentation, so I go directly to the third task here. Sorry. Oh, I'm going the wrong direction. Okay, here. So the work package had 3 subtasks, and one of them was to develop a tool for benchmarking and validation of PQC algorithms. And in order to benchmarking and be able to validate crypto systems for different key sizes, for different parameters, we did a re-implementation of RSA and MLChem. And in addition to that, we implemented different quantum attackers. We used classical attackers and also tested hybrid attacks to test the resilience, in particular of these 2 crypto systems. And the workflow is as follows. So you choose one crypto system, for example, RSA. You specify some parameters. Here in RSA case, you have to specify the maximum bit size of the integer you want to decompose. Then you choose an attacker. For example, let's choose Shor. And then for such an attacker, you can do certain analysis. You can compute an average success rate. You can do the resource estimation, as I've shown before. You can also provide some general information on the algorithm and simulate an end-to-end attack, so from encryption to decryption, and also decomposing or recovering the private key. Then as a last step, we summarize the results in an output file. Can you start the video, please? So, sorry, yeah? There's a video. Yes, now it works, thank you. So we start the program here. We read some input file. Oh, sorry. Oh. Can you go back, please? Okay, let's restart again. Okay, we start our program with some input file. Here we test RSA with a very, very small key size, just 143. We create the private and public key with prime numbers 13 and 11. And then what you can see is we have encrypted the message. Of course, Qrisp is great. With the 2 prime factors, 13 and 11. Apart from that, from the simulation of the attack, we also provided some resource estimation here. So we have 25 qubits and about 130,000 gates. And here you can see the demo of attacking an MLChem system with a key length of 64 and the standard modulus they use in terms of MLChem. And with the attacker LLL, we are for this key size still successful. So we can break the key here and recover the message Qrisp to be encrypted and decrypted. Okay, then we are here. Up to now, we have concentrated here on this red mark part. So we have implemented different cryptographic primitives, RSA, MLChem, etc., different attackers. But of course, our benchmarking suite is not very user-friendly at the current state. So our partners from the open call to NextTech, they took they took care about other parts of this architecture. You can see on the right-hand side, for instance, implementing a GUI, a web service, and an automatic scanning of crypto system a user has on its computer. And I think in the future we will probably join both efforts. To have benchmarking suite that you can use via a user interface, simulate a text, do resource estimation, and have further information. Okay, thank you. That's all.